Welcome to this webinar series on Introduction to Machine Learning. This is going to be a series of 4 to 5 lectures which will introduce you to the field of machine learning, and there is no prerequisite as said already. And I am Sarath Chandar from IIT Madras. Well, before beginning the webinar, I'd like to acknowledge the people from whom I have taken these slides. These slides are not from me. They're mostly compiled from the lecture slides of Hugo, Tan, Steinbeck, Kumar, and Andrew. And most of these animations that you will see are by Subhashri. Well, let's begin. So machine learning started with this question in the year 1950 by Alan Turing, a great mathematician, and who is widely accepted as the father of modern computer science. So he asked, can machines think, in his seminal paper on 1950. So what he meant by this is that, like, can we come up with machines that think like humans? This is a very qualitative question, and he wanted to answer this quantitatively. So to come up with a quantitative answer for this question, he posed something which is widely called as Turing test in the AI community, and Turing test is like this. So this is an experiment where there is a human questioner who can ask questions, and there's a barrier between the questioner and the experiment room, and there is a human source and a computer source. So for every question by the human, the answer might come from the computer or from another human, and the task here is to find which is the computer. Or in other words, a computer is set to pass this Turing test if it is able to convince the human questioner that it is a human. So he proposed this test in 1950 with a conjecture that there will be some machines in the year 2000 which will pass this Turing test by convincing at least 33% of the interrogator or the human questioner, but till date, like, there is no machine which can pass this Turing test. Even though there are some recent news where they say that Turing test has been passed by some machine, but, like, if you take it in a serious note, like, there is no machine which are still up to the level of thinking like human. So this is what the Turing test is, and Turing's introduction of this Turing test led to the development of a new subfield in computer science, which is known as the artificial intelligence. So the major goal of artificial intelligence and any allied fields is to come up with intelligent machines which are artificially intelligent and, like, which can think like human and pass this Turing test. So that's the goal of each and every AI researcher, is to come up with a system that will pass this Turing test. Well, there are many subfields in AI, and machine learning is one such subfield which believes that Turing test can be passed only by coming up with machines that can learn to think. So if you consider artificial intelligence, there are several other subfields like planning, NLP, pure knowledge representation, and so on. But the subfield machine learning believes that this can be achieved only by learning or making systems learn. So this is a very brief introduction to like how machine learning evolved. Like initially, Turing asked can machines think, which resulted in Turing test, which resulted in the birth of AI, and machine learning is one branch of AI. Well, the human brain is a mystery to itself. There are a phenomenal amount of research going on understanding the human brain and simulating the human brain. People widely believe that if we can understand the interior working of human brain, then it is possible to come up with systems which think like human. Why is it so? If you just think about it, human brain is much slower when compared to the processing speed of a modern day computer. But what do you see? A human brain can do things pretty fast than a computer in most of the cases. Not in calculations, but in most of the cases. So why is this happening? It is widely believed that human brain is a massive parallel processor. It like each and every steps can take microseconds, but the computation gets over in 5-10 steps when compared to a fast processor which works in gigahertz, but this has to do 3000 or say 30,000 steps for the same computation. So as I said, the human brain is a mystery to itself. We'll see an example for that. So can you identify the male face in this set of pictures? So there are 4 pictures here, and the task is given to you is to identify the male face here. And take few seconds. I think you don't even need few seconds. You can easily recognize that this is the male face, right? Even though he has a long hair like a lady, but you can easily identify that he is a male. Well, so this is something that you can fastly do. Now can you try this? I want the answer for this 9-digit number multiplied with another 8-digit number. Well, even if I give you a pen and paper, you're going to take maybe 5-10 minutes. If you're fast enough, I think even if you're fast enough, you'll take at least 5 minutes, unless you know some abacus or tricks like that. Well, so what's going wrong? You can do something which is I'm talking about this identification part. Like you can do this thing in a less than a second, but you need 5 to 10 minutes to do these calculations. Think about computers. A computer can give you the result for this calculation in less than a millisecond or microsecond. But to come up with this face identification, it needs days and days of training. And even during the inference phase, like if I give these 4 photos to a machine, it will surely take at least a second or at least a minute to identify who is the male here, and still the machine is not 100% accurate. It will do some errors. For example, in this set of pictures, this lady in the 4th picture might be classified as a male because of her hair, while there is more chance that this man will be actually classified as a female because of this long hair. So computers can do something which you can't do, as in if you take more time to do this calculation, but computer does it in less than few seconds. But it's not good in job that your brain is good at. So what's going wrong here? Think for a few minutes. What is so special about the image identification that computer can't do it accurately? Or what is very clear in the multiplication that computer can do much faster. I'm just giving you a few seconds to think. Well, if you think about it, what is so easy in matrix, like in a multiplication, and what is not so easy in a male female identification is the learning algorithm. Because we know for years and years that, like, there exists a solid algorithm which you follow blindly, which you follow mechanically, you will come up with answer for multiplication. So you have a very clear algorithm which, if you run mechanically, you'll get answer for multiplication. But for the case of face identification, we are not clear how our brain processes that image, and we don't have any equations, or we don't have any formulae that the brain uses to quickly identify the two in less than microseconds whether this is a male face or female face. And if you think about it, humans identify male female with almost 100% accuracy, which means there exists an efficient learning algorithm, an efficient, or in some efficient inference algorithm. I would say it's an inference algorithm. So an efficient inference algorithm that's running in the brain, the human brain, which we still don't know. So the field of machine learning is all about discovering and designing these learning algorithms. So algorithms, when I say an algorithm learns, it means that the algorithm knows, or like gets trained about how to do a particular task. Well, so with this motivation in mind, in this first lecture, we'll see a biologically inspired learning algorithm, which was inspired actually from how human brain works. So this is the very first learning algorithm introduced in 1950s and 60s, which was so popular that people at 60s believe that they are almost close to Turing test, which is actually not the case. And we'll see that. So the very first machine learning algorithm that I'm going to introduce to you is a perceptron, or an artificial neuron. So an artificial neuron is a single neuron unit which is capable of doing some computation. We'll see how a neuron works. So okay, so we'll see how artificial neuron works. So for a neuron, the inputs are given by x1 to xd, inputs are given by x1 to xd. These can be anything. For example, let us consider a classification problem where I would like to know whether it will rain tomorrow. So based on the weather, based on the weather conditions today, based on the temperature today, based on the past history of raining, I would like to predict whether it will rain tomorrow or not. So these features might be something like, the first feature x1 might be whether it has rained today, x2 might be the current temperature, x3 might be the current humidity, and so on. So you have a set of features x1 to x2, sorry, x1 to xd, and you would like to come up with an yes or no answer. Is it fine? So okay, so this is how this artificial neuron works. So given a set of x1 to xd, you multiply each and every feature with some weight. So summation over I, wi xi means that plus you add an additional bias term. So the neuron pre-activation or input activation is given by B plus summation over I wi xi. If you're familiar with the matrix notation, this is nothing but B plus W transpose X. W is a vector and X is a vector, each of size D. So once you have this activation, basically like this is similar to the accumulation phase in the biological neuron. So the biological neuron accumulates the spikes from the neighboring neurons. In a similar way, this particular neuron has accumulated this pre-activation. So after that, like you have to go for the step of activation. So activation is something like g of a of x, where g is some function, the activation function that you are applying on this a of x. So here the w are known as the connection weights, and b is the neuron bias, and g is the activation function. One second. Okay, so B is the neuron bias and G is an activation function. So now we need to know what is this bias and activation function. I'll explain them in the next few slides. So before that, just keep in mind that perceptron is basically a single unit which takes weighted sum of the features and adds some bias to it and make decisions based on the activation. Well, so the decision boundary for this neuron is like this. So basically you have some decision boundary which is actually decided by this bias. That is why we have the bias. So based on the bias, we have a decision boundary, and things at one end of the decision boundary can be S, and things in other end of the decision boundary can be no. And the range of the output is actually determined by the activation function. For example, in this decision boundary, the range is from -1 to 1. So I can safely say that till 0 it is going to be no, and from 0 to 1 it is going to be yes. So in that case, this entire down region will become no, and this region will become yes. So here we have assumed that there are only two features, x1 and x2. So when I have two features, x1 and x2, and when I have some activation function which ranges from -1 to 1, I set up a threshold at 0 saying that any input instance which has activation function greater than 0 will be classified as S, and any input instance which has the activation function less than 0 will be classified as no. If you think about it, this decision boundary is linear. Why is it linear? It's because of this activation function. So you have a bias, and that bias determines the point at which you cut the decision boundary. So we'll talk more about the activation function. We'll see several activation functions which can be used to fill this place. The first activation function that we are going to see is g of a is equal to a. So g of a is equal to a means that you take some, like you have some pre-activation which is b plus w transpose x. You just give it like you just give it as the output without any additional operation. So it performs no input squashing. Like if you see if the input is -1, output is also -1, and so on. So this is not very interesting. We will see some other activation functions. The next activation function is sigmoid activation function. So the sigmoid activation function squashes the neuron's pre-activation between 0 and 1. If you see here, like the range starts from 0 and it ends at 1. This is always positive This is always positive. Why? Because it's between 0 and 1, and this is always bounded since it can't go below 0 or above 1. And the nice property of this function is that it is strictly increasing. So the sigmoid function is mathematically expressed like this: g of a is equal to 1 by 1 plus exponential of minus a. So this has range from 0 to 1, and we'll see the next activation function, which is tan h. So tan h of a is actually given by this formula: exponential of a minus exponential of minus a divided by exponential of a plus exponential of minus a. So there is a question: so can this method be used only to give a binary result, as in is it only an yes or no classification? Where I'll come to that point shortly. As of now, we are considering about an yes or no problem. We'll see how to generalize that. Well, so this is the formula for tan h function. This actually squashes neurons pre-activation between -1 and 1. So if you see, the lower bound is -1 and upper bound is 1, and obviously it can be positive or negative, but still it is bounded and strictly increasing. So this next function is rectilinear function. So rectilinear function is given by max of 0, a. So what this means is, whenever I get a pre-activation which is a negative number, I'll put 0 as the output. Whenever I get a positive number in pre-activation, I'll just output that number. So this is bounded below by 0. This is always non-negative, but there is no upper bound. Again, it's strictly increasing. I guess it's strictly increasing from 0. Before that, it is strictly non-decreasing, and it tends to give neurons. So the major advantage of going with rectilinear activation function is that we tend to give neurons with sparse activities. By sparse activities, I mean that most of the time it will be 0. It will be emitting 0, and it will emit numbers like very rarely. This has several applications, and we'll see them later. So what we have seen so far are, I guess, 4 activation function. This is the constant activation function, and this is the sigmoid activation function from 0 to 1, and this is the tan h activation function, which is from -1 to 1, and this is a rectilinear activation function, which will emit 0 when there is a negative pre-activation and emit the same pre-activation when it is positive. Well, so we'll try to answer this question, like, what can a perceptron actually do? As there was a doubt by, I guess it's Sai, so like, can this do only binary classification? Well, it could do binary classification. So with a sigmoid unit, which actually gives you output in the range 0 to 1, you can consider the output as a probability. Since the sigmoid is from 0 to 1, whatever output you have, you can consider it as the probability of y is equal to 1 given the input. So there are 2 classes, 1 and 2, and whatever output you get is the probability that y is equal to 1, and the probability for y is equal to 2 can be the 1 minus output. So this classifier, the single neuron classifier, actually this perceptron with sigmoid, is known as the logistic regression classifier. If the output is greater than 0.5, then that means that it is highly probable that the given input is, like, the class is y is equal to 1. So if the output is greater than 0.5, you predict class 1, otherwise predict the next class, which is 0. This is a very simple idea, and this can be extended to tan h also. As I told you already, So tan h starts from -1 and it goes till +1. So I can set up a boundary at 0 saying that when it is greater than 0, the class is 1, and when it is less than 0, the class is 0. So this can be done for, like, the idea of coming up with a binary classification using sigmoid can be extended to tan h also like this. But one thing that you should remember always is the decision boundary is linear. When you have, what it says is, like, when you have, you can easily classify two regions like this, or two regions like this, or two regions like this, or two regions like this, and so on. So the decision boundary is going to be linear, and this has several limitations. But in 60s, when people were very much excited by this perceptron algorithms, they started claiming that perceptron is a universal learning algorithm and it can do, like, each and every single task that you want it to do. But what can a perceptron actually do? As I have told you already, like, it can solve linearly separable problems. For example, consider the first problem, which is OR problem. So given x1 and x2, the Boolean variables, I want to compute the OR function. So 0 plus 0 is 0, 1 plus 0 is 1, 1 plus 0 is 1. So this 1 belongs to one class, 0 belongs to one class. As you can see, there is a linear line which separates 0 and 1. Fine. Similarly, consider the second problem. Here the second problem is AND of x1 bar and x2. So I have x1 bar and x2. So x1 bar for 0 will be 1, 1 and with 0 is 0, 0 and with 0 is 0, 0 and with 0 is 0, 1 and with 1 is 1. So again this has a linearly separable, again this is linearly separable. If you consider the next problem, this is also linearly separable because you have some line which separates the first class and the second class. Well, so it's exciting. We have some algorithm which can pretty much do these simple problems. But wait, so in 60s or 70s, I don't know, what happened is Marvin and Minsky came up with this simple XOR problem, and they proved that perceptrons are not capable of solving this very simple XOR problem. What is an XOR problem? XOR problem is basically the same as the previous problem. Like, you have two features, x1 and x2, and you want to compute the XOR of x1 and x2. If you see this input space, you need some classifier which will correctly classify this as first class and the rest as second class, right? So here you cannot come up with a single line which separates class 0 and class 1. This is not linear. So for this very simple nonlinear problem, perceptrons are not good enough. Or in other case, what you can do is you can come up with a perceptron which classifies like this with 75% accuracy. So it's going to classify this as triangle class and all these three as a circle class. Or you can come up with another perceptron maybe like this, but you cannot come up with a perceptron which does this just 100% with 100% accuracy. So that's the limitation of perceptron, and soon people realized that, like, they are nowhere near to passing Turing test because they have a learning algorithm which can't even solve the XOR problem. Forget about any other real world problem like face identification or, say, image search or video search. So like it's like the research in perceptrons is completely stopped for few years, at least for the next 2 decades. And in 1984, Geoffrey Hinton from University of Toronto came up with an idea, and he said that wait, it is not that perceptron is completely stupid. Maybe, well, since you have only one, like since it's a single neuron, it's not capable of doing complex tasks. But if you give it, like if you feed it the correct input, it will always give you the correct output. As in, like if you feed it the better input, like the modified inputs instead of the usual inputs, such that you transform the input space from a nonlinear space to a linear space, then the perceptron can perform better. Because we know that the perceptrons work well in linear space. So what he suggested to solve XOR problem is you can write XOR basically like you have x1. Sorry for the slow writing. You want to compute x1 XOR x2, which can be written as x1 bar x2 plus x1 x2 bar, right? We know this basic transformation, like x1 XOR x2 can be written as x1 bar x2 plus x1 x2 bar. Okay, so what he suggested is instead of giving x1 and x2 as input to the perceptron, give x1 bar x2 and x1 x2 bar to the perceptron, and you have a classification problem which has a linear boundary. So there is a question. So what about classifying based on whether it lies on the line rather than the boundary? Well, it has some issues. So the question is this, like why can't you come up with a classifier which classifies based on whether it lies on the line? So if you think, okay, I'll come back to this XOR problem. So if I have a classifier which classifies with triangle when it is in this line, and it's a circle when it is not in the line, just think about it. If you have only 4 training instances like this, fine. The approach that you say will work only when you have all possible training instances. Say I have some, sorry for the poor diagram, say I have some examples like this and some examples like this, and I decide to come up with a classifier which says that anything that lies in this line are classified as circle. But what if there's a test instance which is slightly deviated from this line? It should be classified as cross, right? But the simple thing that you could have done is to come up with this linear classifier. I hope that explains the answer. Well, so this is the idea by Hinton, that you modify the input features and give it as input to the perceptron. Well, that is going to give you the correct answer for XOR problem. Or in other words, if you think about it, what he suggests is to use a single perceptron to do this AND. We know AND is linear, and another perceptron for this AND, then a third perceptron to do XOR. So it's something like this. You have the first perceptron which takes x1, which takes x1 and x2, and this is going to give you the AND of the first AND. Similarly, you take the second perceptron, which also takes the input from the same inputs x1, x2. Now you feed in these two ANDs to another perceptron. So here comes what we call as neural network. So this is basically a network of perceptrons. Like you have a perceptron here which gets input from the other perceptrons. So that's the concept of neural network. So a quick note before beginning neural network. I have explained you what a perceptron is, but I have not explained you in detail how to train a perceptron, which is something out of scope of this webinar. Like we will be concentrating mostly on the major learning algorithms, and the training part, like I'll give the intuition for training each and every algorithm, but we won't get into the details, the technical details of it, since it is just an introduction. So the next learning algorithm that we are going to see is neural network. A question before that. Well, so okay, so we'll continue. So the second algorithm that we are going to discuss is neural networks. As I gave the intuition already, like it's basically a multiple layers of neurons connected in a structured way. So basically you have this inputs as usual, x1 to xd, and the bias term. If you think about it, this is one single artificial neuron or perceptron that we had initially. So what we are going to have is multiple such perceptrons. So there are multiple perceptrons connected to the same set of input features, and this layer is known as the hidden layer. So you have the input layer, you have a hidden layer which is a bunch of perceptrons, and again these feed into another perceptron which is in the output layer. The computations are almost similar. So for each hidden layer, the activation is given by the bias plus W1x. And that's a pre-activation. The hidden layer activation is given by G of A of x. So for each neuron, you have this separate weight matrices and the bias term. Then the output layer is given basically from x, you go to this h of x, which is the hidden representation. Now you have h of x, which consists of d terms, and you give, like you do another activation, which is f of x, which is equal to the output activation of b2 plus w2 transpose h1 of x. If you just notice, like there are two activations, the hidden layer activation and output activation, which I call it as G and O, and it is not necessary to have the same activation function in hidden layer and the output layer. It is not even necessary to have the same activation function within the perceptrons in the same layer. So each perceptron can have different activation function and specialization, different task. So this is how a neural network looks, and like we will see how to use this for a multi-class classification problem. So far what we have considered is, like we have a binary classification problem where you just need to say yes or no, and whatever like since you are using a sigmoid at the top layer, you will get some value between 0 to 1, and if it is greater than 0.5 it is first class, if it is less than 0.5 it is second class, right? So for multi-class classification problem, what is the requirement? We need multiple out. One simple solution is this. So you have multiple outputs. For each class you put an output, and we would like to estimate the conditional probability, like what is the probability of that class given x, right? So what can be done is to use a softmax activation function at the output. What is softmax activation function? So softmax of A is given by exponential of A1 divided by summation of exponential of AC. So this is something similar to normalization. For example, consider I have 3 classes and the activations that I am getting are 1, 1 and 1. So how will you normalize this? So one simple way to normalize this is, so you can put 1 by 3, 1 by 3, 1 by 3, right? So each becomes 1 by 3 and we have a valid probability. This sums up to 1, like 1 by 3 plus 1 by 3 plus 1 by 3 is 1. But what is the guarantee that it is going to be positive if you just do this a term divided by that term, divided by the sum? So what if I have a minus 1 here? Then you will have minus, the first probability will be minus 1 divided by 2 plus 1, which is 1, which doesn't make sense, right? So you need something which is strictly positive. So that is the reason why we take this exponential, like exponential of a term is going to be positive. So like you do exponential of A1 divided by exponential of, like sum over exponential of other terms, like the all term. So now if you consider this neural network, so let us assume that I have 3 classes, then I will have one output neuron for class 1, one output neuron for class 2, and another output neuron for class 2, and all these 3 will have the softmax activation function. Is it fine? Well, now how will you predict which is the actual class? So now you have a softmax function, which is the probability distribution. Let us say I have probability 0.5 for the first, like for a given test instance, I have probability 0.5 here and 0.2 here and 0.3 here. So now my prediction will be that this is the first class, since that's the class with highest probability. Well, so what we have seen so far is a 3-layer neural network, but it can also have multiple hidden layers. For example, if you consider this neural network, it has 2 hidden layers. So from the input layer, I go to the first hidden layer by the usual wx plus b. Then you have some h1 of x. From h1 of x, you consider that as the input and go to the next layer, which is h2 of x, and you proceed until the end where you have a softmax layer, if it is a classification problem. Well, so what's the capacity of this neural network? Well, so what we have seen is that a perceptron has a linear boundary. But if you take a neural network, say consider this neural network, here you have, just consider this perceptron. This is the decision boundary for that perceptron. It is a linear boundary. Similarly, you have the second perceptron, which has this decision boundary, which is again linear. But what I'm going to do is combine these 2 boundaries for the final perceptron. So once I combine these 2 linear boundaries, so I get a non-linear boundary like this. Or in other words, this is like the capacity of a neural network is much higher than a single perceptron. So we'll see some more examples. Consider this example. Here I have 4 perceptrons in the hidden layer, and this is the boundary for the first perceptron, this is the boundary for the second perceptron, this is the boundary for the third perceptron, and this is the boundary for the fourth perceptron. And when you take a union of these boundaries, you get a nice bump shaped classification region. Well, now consider this neural network. So this is just a neural network which has, say, 5 hidden layers, and when you take a union of these 5, you get an even more general decision region like this. See, if you consider here, like you have region 1, region 2, and a part of region 2 inside region 1, and another part of region 1 inside region 1. So if this is very complicated and you need multiple perceptrons to do this, and a single neural network does that. Is it fine? Well, so the capacity of a neural network is formally just a second. Screen has shop. Sorry for the interruption. Well, so the capacity of neural network is formally defined by this universal approximation theorem. So the universal approximation theorem, as stated by Harnack in 1991, goes like this: a single hidden layer neural network with a linear output unit can approximate any continuous function arbitrarily well given enough hidden units. So you should just give me a second. So you must note this point that, like, given enough hidden units, so based on the complexity of the problem, if I have a less complex problem, I need less number of hidden units. If I have a very difficult problem, I need more number of hidden units. But given enough hidden units, a single hidden layer neural network can very well approximate any problem, like any continuous function. So the result applies for sigmoid and tan h and many of the hidden activation functions. This is a good result, yeah, but it doesn't mean there is a learning algorithm that can find the necessary parameter values. This says that there exists a parameter configuration. There exists a set of ways for the neural network which can very well approximate this continuous function, but it doesn't tell you explicitly, like, the learning algorithm which can learn this weight appropriately. Well, that's a trick in every learning algorithm. Like, even though you know that the classifier is capable of doing something, but you need to search for a correct parameter specification, and that is what the learning algorithm does. So the goal of learning algorithm is to learn a set of parameters for a classifier. In this case, it is a neural network. So to learn a set of parameters, the weights and bias of the neural network, which very well approximates the given target function. Well, so as I told you in the beginning, this is an algorithm which is inspired from biology, and the main reason for coming up with this layers of neural activation network is like coming from the visual cortex. If you see the visual cortex of human brain, basically, like, from the retina you get information to this B1 layer, which has simple visual forms, which can recognize simple visual forms like edges and corners. So from there it goes to the V2 layer, then V4 layer till AIT layer, and if you see what each layer does, This is what it does. So the first layer, the V1 layer, like it does some simple visual form, like it is able to recognize some simple visual forms like edges and corners, and the layer V4 has intermediate visual form. It can recognize intermediate visual form features, groups, etc. And AIT is responsible for high-level object descriptions, faces, and so on. For example, when you see a human face, V1 layer will detect all these edges, the circle, lines, and so on, and the V4 layer will join these edges to form nose, mouth, and eyes, and the AIT layer will actually say that it is a face. So what this tells us is that the brain, the human brain, works in a layer by layer fashion, where each layer has its own set of abstractions which are not necessarily known to the higher layer, and each layer just passes some information to the higher layer for the effective decision to be taken. So this is how a single biological neuron works, and now you should be able to come up with an analogy for the biological neuron versus artificial neuron. So if you see a single single biological neuron, it has some axon, and the axon is connected to a region called synapses, and the synapses is a region where other neurons pass some information. Sorry. So the signals are received from the dendrites. So the signals are received from dendrites, the other neurons pass information here, and some form of computation is done in the cell body, and it passes the information through axon to synapses to other neurons. So if you compare this with the artificial neuron, so these are the inputs from the features, and the computation done in the biological neuron is equivalent to the pre-activation and activation, and the signal transmission is equivalent to sending your input to the next layer neuron. So this is where like people took the inspiration for artificial neuron, and I'll quickly give you a basic intuition for training a neural network. And the training a neural network is basically done by backpropagation. So backpropagation means that you basically consists of two phases. One is a forward phase. In the feed forward phase, you give input to, basically you have an input, you pass it to through the network till the output layer. So once you go to the output layer, whatever output you have, compare it with the actual output and train accordingly. So I'll go through this animation, and which will help you to understand how backpropagation works. So basically I have some training instance x comma y. So given x comma y, I'll feed x to the input layer, and from the input layer we know, like, first initially you just random, like you need weights here, right? So you randomly initialize these weights and these weights. So you have random weights, perform the computation, you'll go to the hidden layer, from the hidden layer again use the random weights and go to the output layer. So once you come to the output layer, you have some output values. You all consider this as a binary classification problem. So you have this is the probability for the class 1 and this is the probability for class 2, and let us say that the actual output should be this. It's a first class, so the output should be 1 0, but the actual, this is the actual output that you should get, but by forward propagation you might have received some output like 0.7, 0.3. Fine. So my current network configuration tells me that the probability for the first class is 0.7, probability for the second class is 0.3, but the actual probability that we know from the training instance is 1 and 0. So what I should do now is to backpropagate the message that no, this is not 0.7, this is actually 1, and similarly back propagate the message that this is not 0.3 but this is 0. So that is what the backward phase of the training does. Like, you compute the feedback. This feedback is usually the difference between the actual value and the computed value. So in this case, the feedback is 0.3 and 0.3 and minus 0.3. You compute the feedback and give back, like basically give the feedback to the hidden layer. But if you give the feedback to the hidden layer, as you can see from the animation, the gradient that you're computing is going to decrease because you start with a place and you split the gradients accordingly. Or in other words, for this particular neuron, there are 4 neurons responsible for the computation, and you are splitting the responsibility equally, or you're splitting it based on the weights, and the gradients are going to be decreased, and it is going to further decrease when you go to the input layer. Well, this algorithm works very well when you have a 3-layer network, or in other words, a network which has the input layer, one hidden layer, and output layer. But what happens when you do backpropagation in a neural network which has more number of layers is this. Consider this neural network which has 5 hidden layers. 1 second, let me check if there are any questions. Well, so consider this neural network which has 5 layers, like 1 input layer and 3 hidden layers and 1 output layer. So I am going to do forward propagation. Well, it's fine. I get the feedback. Now I'm sending back the feedback, or I'm back propagating the feedback to the first hidden layer, like the top hidden layer, middle hidden layer, the first hidden layer, and the input layer. Well, if you see, when it reaches the first hidden layer, it is almost 0. The feedback that you're giving is almost 0, and it's almost negligible. So what will happen is, if I initialize this part randomly, sorry, the poor handwriting. So if I initialize this part randomly and start my training, it is going to be almost close to that random configuration, even if I train, because there is no proper feedback from the top to this layer, and this results in like almost no change the weights in the lower layers. So what people observed in 90s is that when they use a hidden, like a neural network with more than 1 or 2 hidden layer, the performance was actually poor. Well, people thought that that's the end, because like a 3-layer network performs well, that's fine, but definitely for a much complicated problem, you need more number of layers, or you need more number of neurons to generalize well. But when you go to more number of layers, it's not working. It's like, it's as if you don't do training at all, right? Like you have a set of random weights, and anyway, like almost half of the network is not updated, and it's as good as having a neural network with random weights, which will obviously perform bad. So again, the field went down until 2006, when the solution for this issue in backpropagation was proposed again by Geoffrey Hinton from Toronto, which resulted in the emergence of deep learning. So like before that, there's a question: how will the backpropagation increase the accuracy? So if you consider the example that I told you, in this example, when I backpropagate, I will update the weights in such a way that if I compute the weights again, like if I compute these values again, it will go close to 1. This will go close to 1 and this will go close to 0. And I'm going to continue this and I'm going to iterate on this again and again until all my values are close to the actual values in the training data. This is for the again, this is only for the training data, and for the test data we don't know what will happen, and usually neural networks generalize well for the test data. I hope that answers your question. Well, so the solution for this issue in backpropagation is proposed in 2006, and there are several solutions, and we'll see one simple intuitive solution based on autoencoders. So an autoencoder is basically a 3-layer neural network where the input layer is equal to the output layer. So the same input layer is in the output layer with a hidden layer which is smaller than the input layer. So basically I have some x, I'll compute h of x, then I will reconstruct x from h of x. So it is an encoder followed by a decoder. What encoder does is sigmoid of b plus wx, and what decoder does is sigmoid of c plus w star h of x, and the weights are usually tied together. Like whatever weight you have here, this is the transpose of that. So say I have 1k features, so I have 1000 features, and I'll compress it to 100 features, just 100 features, and I will reconstruct the same 1k features from the compressed h of x. So in other words, this acts like a dimensionality reduction system where you reduce the dimension from 1000 to 100 and then go back to 1000. So what people observe is that this reduction to 100 dimension is actually very helpful. So this compression is helpful in the sense that it projects the data into some space which is more meaningful. So that's a quick definition of what an autoencoder is, and we'll see a way, like a solution for this issue in backpropagation using autoencoder. So whenever you have like more than one hidden layer, it's considered as a deep neural network, and like we are going to see an alternate way to train deep neural network, which we call as deep learning, in contrast to the normal backpropagation. So what I'll do is I'll initially start with an autoencoder. So this is my set of features. I'll set up an autoencoder and perform the compression and come up with this hidden representation. Then I will remove the top layer. So now I have the first layer, then the compressed layer. Then I will set up another autoencoder with this hidden layer as the input. So now I have projected data from here to here. Now set up another autoencoder and learn this hidden representation. Continue. Now I remove this top layer and set up another autoencoder and so on. So I will continue this process until I feel that I have come up with some place where like I have actually compressed the data enough. So once I have this representation, I'll again remove the top layer. So I have the first representation projected to the second representation, projected to the third representation, to the fourth representation. Now I'll just replicate this to the top layer. So now this is going to be a very big autoencoder because the input is equal to the output, and all the weights in the bottom are tied up with the weights in the top, and I'll do ordinary backpropagation here. So like for every autoencoder, the training is basically the reconstruction error, right? Like if you consider this autoencoder, how will I train this? I'll train this to reconstruct from here to here. from here to here. Similarly, in this autoencoder, like the final autoencoder, I'll train to reconstruct from here to, sorry, to here. Fine. So this first phase of like greedy layer wise training is known as pre-training, and this last phase, like the last phase where I actually do a common backprop, is known as fine tuning. Why is this working? Or in other words, why is this better than a usual backpropagation? Take few seconds and think about it. Well, so the answer is this. So what the major issue with backpropagation was that the weights are randomly initialized and they are not getting updated frequently. So like there is no use from the training, right? So what this deep learning algorithm does is basically initialize the weights in an intelligent way, or initialize the weight in a greedy way, such that the initial weights that you start for this backpropagation are not random and they are almost close to the global optimum. So you almost have the optimal values, and all you need to do is to do a bit of fine tuning, which can be easily done with backpropagation, because for fine tuning you just need to update the weights in a very small amount, which is what the backpropagation actually does. So this is one intelligent idea, and there are several other ideas and methodologies which are recently evolving to train neural networks, like the deep neural networks, in more intelligent fashion. Well, so what we have seen today is to do classification with two different biologically inspired neural algorithms. One is the perceptron algorithm, and the next one is the generalization of perceptron, which is the neural network. And we have seen why it is difficult to train a deep neural network, and we have also seen one approach to solve that issue. Again, a note to remember that we still have not get into the technical details of how to train a perceptron or how to train a neural network, but all we have learned is the intuition of how it works. And I hope that if you go back and read the training procedure, you should be able to understand. Well, I'll stop the first lecture here and we'll continue the rest in the next lecture. So it's time for questions. If you have any questions, or if there are any pending questions in the chat box, I'll try to answer. So I guess I have answered most of the questions. If you have any questions, please post it now. So there is one question which says maybe there might be an abstraction level inbuilt in humans. Yes, of course, and we are still trying to understand that abstraction, and that's what every machine learning algorithm is trying to achieve. And I guess I have answered the question by Sarath already. So do we find in the complement, feed in the complement values of, or use two more perceptrons? So I guess you should be able to answer it now by yourself. Like we have a layer, like multi-layer, we'll have a multi-layer perceptron where the complement values are fed by a separate perceptron. But doesn't well. So are there any other questions? Well, so okay, that's the end for the first lecture, and we'll see soon in the second lecture in the webinar series.